Uh, what I'm going to do today is talk about different types of piers used in Alaska and the rest of the country as well, and talk about the magnitude of the ice loads on those bridge piers. That is what we apply to the bridge piers as part of our bridge design. And I'm going to do that by talking about a handful of bridges throughout the state. So let's start by jumping right in and talking about a bridge that is out of the norm, the Safety Sound Bridge near Nome, Alaska. It was built in the late 1970s. It is a pretty standard highway bridge, pre-stressed concrete girders, steel pile extensions that support cap beams. This is the bridge prior to about 1995. In the mid 1980s, there was a very unusual, or at least unusual for what we thought about for the design of the bridge, event in that the ocean ice froze relatively solid. There was a long stretch of pretty windy weather, so we didn't have the insulating blanket of the snow. So the ice thickness kept getting greater and greater, greater than the bridge was designed for, or at least that we had designed the bridge for. And that same wind force was sort of pushing the ice inland and taking the bridge with it. So although it's hard to see in these photos, the bridge was translated at some of the piers about 1.5 feet transverse to the long axis of the bridge and about 1 foot along the length of the bridge. So that's pretty significant. The bridge almost had a collapse scenario, but fortunately a snow machiner was driving by and saw this and notified the department, and we could get out there and fix it. So here's the bridge after the repairs were completed. You can see we've added outboard piles. We've put some sort of stiffening up near the upper portion of the piers to effectively shorten the piles, making them stiffer and stronger. The original design from the 1970s, there were no field measurements to work off of, so they used local observations, anecdotal information, and some oil industry estimates that Alyeska had developed. I'm not sure why they were all the way over there at Nome, but they had some numbers for us. And then using the code requirements of the day, the ice forces on the pier were estimated to be as shown, 108 kips. So a kip is 1,000 pounds. So 108,000 pounds transverse to the long axis of the bridge. 21.6, that's pretty precise. That's an extra decimal there for something like ice load, but 21.6 along the length of the bridge. And the biggest concern was vertical ice loads. That is, we've got this large, essentially infinite sheet or slab, if you will, that's supported on an elastic foundation. That's the water, the ocean. And as the tide would come in and go out, that weight of the slab, the ice slab, would impart a vertical reaction onto the pier. So it was sort of like frost jacking, but not really. But anyway, 530 kips. To put this in perspective, a legal highway load, like an 18-wheeler rig that's just at the legal limit, would be about 80 or 90,000 pounds. So this bridge was designed for a lateral load on the outboard pile of about one tractor trailer load of weight, about a quarter of that along the length, but about 4 or 5 of that, maybe a little more vertically. So vertical was a big deal. The lateral wasn't considered to be too much. But after we had that movement of the bridge and the ice load, we could then measure the thickness directly by coring through. And the ice thickness was measured at the time of the deformation of about 6 feet. That's better than twice what we had estimated for the design. And back calculating the ice force, knowing the deformation in the bridge, right? We know the strength of the bridge and the stiffness of the bridge, so we can work backwards to figure out what the force was to push the bridge to that position. It wasn't 108, but 1,500 kips. So roughly, 15 times what the bridge had been designed for, 50 times roughly in the longitudinal direction, and only slightly greater in the vertical. The reason it was greater in the vertical is that the size of the pier had increased. We went from 3 piles to 5. That had a bigger footprint, and consequently that force went up. So our estimates for vertical actually weren't so bad, but for the others, not so good. The AASHTO LRFD bridge design specifications is the code by which all bridges in the US and many other countries are designed. Article 3.9 addresses ice loads on bridges, and I'll share with you some of those pages. The red highlighted articles, these are the ones that typically govern the design for ice loads on bridges in Alaska. Now, all the other ones are considered, and you can see there's issues like hanging dams and vertical forces like we just talked about due to this ice adhesion, this bending of the ice plate. But the ones that are most often controlling for the lateral design of the bridge pier are those highlighted in red. There's about 8 pages, I think, on ice loads, which sounds like a lot, but it's a 2,000-page document. So in the scheme of things, that's pretty skinny for the bridge code. So that's a way of saying we don't really know much about ice loads. And these provisions that are included still in the AASHTO code have been around since at least the 70s without much change. I'll just flip through the pages so you can look at the code. You can perhaps look at them in detail if you have any interest in them later, but they're relatively simplistic algebraic expressions, so I'm not going to derive any of those calculations. The next bridge that I'll talk about is the Gakona River Bridge near Glen Allen, sort of kind of. It's near Gakona, but it's at the confluence of the Copper River. The old bridge, the bridge that has since been replaced, was a large span truss that you can see in the photo. And this photo is taken during breakup, and you can see the big beat up ice and the debris in the ice, and it is just a foot or two below the low chord of the truss. And to be clear, we did not design this truss or really any bridge to be hit at the deck level, the superstructure level with ice forces. They're very large and they're a hard thing to accommodate. So your best bet is to raise the bridge up so that you don't have to contend with the ice. In this photo, the ice is not hitting the bridge, but the ice has struck the bridge or has contacted the bridge prior to its replacement. Another kind of interesting issue with the same bridge that you can see here, it might be a little hard, but if you look, you'll see it. The bridge is oriented such that the shadow and I guess you could say is always in the same place. That's not completely true, but is frequently in the same place. Consequently, sunlight can't get to this part of the river below the bridge. And you'll see the ice underneath the bridge doesn't melt out at the same rate as the ice around the bridge. So you get this ice dam or this ice weir that forms around the bridge. So that's not necessarily a good thing, as it has a tendency to make ice jamming and ice collection and just debris collection in general more treacherous, more of a design consideration. Well, the truss bridge was in pretty poor shape. It was restricting weights and heights and widths of various vehicles, so we replaced it with a standard highway bridge. As we talked about today, during construction, we'll build a temporary bridge, typically upstream, like is in this photo, to accommodate traffic while we destroy the old bridge and put a new bridge in its place. That is, we'll put it on the same alignment. That's not always the case. Sometimes we'll put a new bridge on a new alignment, but oftentimes we've got the ideal alignment, so we want to replace the bridge on its existing alignment. During the installation or during the service life of the temporary bridge, there was another large breakup event, and you can see that some of that ice is being backed up by the temporary bridge. And one of the questions that we had earlier had to do with what do you do in this event? What happens? We've got a temporary bridge that's resulting in this ice jamming or back water back ice event. And the answer is, in theory, the contractor's on site all of the time, and that we can put them to work to remove this ice as it occurs. So they might take heavy equipment, reach over the side and sort of drag it to the banks or push it underneath the bridge or break it up or something. That's generally a successful approach, but not always. In any event, we built a new bridge, again, a pretty standard pre-stressed concrete superstructure. And the type of pier that's frequently used in Alaska is this pile extension bent. So this is one of your learning objectives, is to learn the jargon that Alaska uses for our pier configurations. The jargon's probably different from state to state, but in general, these are agreed upon jargon. So where we have these pipe piles that extend deep into the ground, they extend out of the ground and support a concrete cap beam, in turn supports the superstructure, that is the girders and the deck that the cars drive on. These steel pipes are filled with reinforced concrete, which further stiffens and strengthens them up and allows us to make a connection between the cap beam. So we call these pile extension piers or pile extension bents. We kind of use those interchangeably. And we like them. They're fairly inexpensive. They don't require a cofferdam, that is a structure built around them that has to be dewatered to get access to the ground, to drive smaller piles and a cap beam and columns that come off of that. So they're, in general, considered to be more environmentally friendly. One of the loads that we consider on these piers is ice loads that we've talked about. And here's just some sample calculations. And they're, as you can see, pretty simple calculations. One of the input parameters is the design thickness for the ice. And we typically rely on our hydraulics engineer, in this case, Mike Knapp, to give us that estimated thickness. We might use Stephan's equation as approximation or a check, but in the end, we'd like to have real measured data. We also need to know the effective crushing strength of the ice, which isn't really the same thing as the compressive strength of the ice. It's sort of a back calculated force that could be anywhere from, according to the code, 8 KSF, 8 kips per square foot, 8,000 pounds for a 1 square foot interface, all the way up to 32,000 pounds per square foot. And it also has to do with the shape and style of the pier itself. So a round pipe might be different than a square column, might be different than a rectangular pier. Anyway, you plug those numbers into the equation and out comes a force. In this case, the design transverse force is 355 kips. Remember safety sound, we started at 108 and I think we ended at 1500. So we're about a fourth or so of the safety sound value for the Gakona River Bridge. That's transverse to the long axis of the bridge. And then along the length of the bridge, it's 105 kips. So that gives you a feel for the magnitudes of loads we're talking about. 400 kips transverse and about 100 kips longitudinal. As I mentioned, we like these concrete filled pipes. They're real strong, they're real stiff, and they're great for seismic, which is really one of our most controlling design considerations for bridges. This is a laboratory photo. Below this cap is soil, and we're pushing and pulling back and forth on this concrete filled pipe until we fail it, and it's real strong. So the good news is that we can resist large ice forces. Okay, now I'm really going to speed up. This is the Tanana River Bridge near Tok. This is the old bridge, a cantilevered truss, and behind it is the new bridge, the high, again, a pretty standard highway bridge. The old bridge had a wall pier. That's what we call in Alaska. Now, in some states, a pier is calling something a wall pier would be redundant, that a pier is a wall in their jargon. So a wall pier would be like a wall support. So they wouldn't make sense. But in our state, we would call this a wall pier because it's like a wall. It's got relatively thin and along the length of the bridge and really the full width of the bridge in the transverse direction. Now this wall pier at the old Tanana River Bridge had this sloping nose on it, an icebreaker nose. It was specifically designed and put there so that ice would ride up on that nose and then it would bend and break over that nose. So it didn't crush, but it failed due to bending. Now, it's a challenge for us to do this type of pier today. One, the in-water work requirements are much more significant. We'd have to build a cofferdam, that is a box, in the water, dewater it, get down to the ground, excavate, drive piles, build a footing, put this wall pier on it, and then continue up, take the sheet piles or whatever the cofferdam is out. It's expensive, it's time consuming. Additionally, when we have a sloping nose, whether it be sloping piles, we call battered piles, they're very poor performers in seismic loads. So they might be helpful for ice loads and giving a stiffness, but under seismic demands, they're terrible. They have failed. They're notoriously bad, and states like California, for the most part, have outlawed battered piles, which Alaska does as well. The bridge that we replaced it with has a hammerhead style pier. So you can see it kind of looks like a hammer up on top, and it's just a large diameter, in this case, hexagon of a column. I think it's an octagonal column that is supported on a larger foundation below. And both these structures are designed for the ice loads, but the hammerhead pier, like the pipe pile extension bent, resist the ice loads by crushing, by an effective crushing strength. So when the ice hits the bridge, we don't really care how big the ice flow or sheet is. We just look at the effective crushing strength of the ice. We call it a limit state design, that it can't get any worse than what it would take to crush the ice, against the pier. So on the new Tanana River Bridge, the transverse load is 1,450 kips, again, transverse to the long axis, and 420 kips along the longitudinal axis. So compared to Gakona, which was 355, we're what, four times, 5 times, roughly speaking, that same load. The ice is thicker, the pier is larger diameter, so it has a greater cross-sectional area to hit, and those are consideration. The effective crushing force for Tanana River is greater than Gakona. That is, when the ice gets to Gakona, we think it's a little more broken up than when the ice gets to the Tanana River Bridge. Another bridge is the Kenai River Bridge at Soldotna. I think someone mentioned this location and the problems the ice has there. The old bridge had a hammerhead type of pier. And as it gets wider, again, it becomes sort of a wall pier. So this is sort of a hybrid. The new bridge has a very wide wall pier. And what I'm showing in these photos is there's a temporary bridge upstream. And then you can see there were some spare piles beside the highway bridge, the new bridge, that were used for temporary supports. On January 27th of 07, they were there. And then there was a big ice event, an outburst event. And on January 30th, they were gone. Ice loads are real. I don't know where those piles went. I'm not sure the contractor ever found them, but it's a real deal. And again, this definitely a wall pier in Alaska jargon, so wide structure, relatively thin. The design transverse force 2,500 kips, so now we're about twice what was at Tanana, and the longitudinal 1,300 kips. And again, this is in Soldotna, and the Tanana River is up at Tok. So you might be thinking that shouldn't there be greater ice forces at Tanana than there would be at Tok? Well, it just doesn't work that way. You know, it's a function of ice thickness and effective crushing strength and the geometry of the wall. So just latitude alone is not sufficient to determine your ice force. And finally, the Yukon River Bridge. This is I'm sure most of you have seen it if you've been to the Yukon. It has wall piers that are designed for 2,600 kips of transverse force, pretty close to what Soldotna is designed for, and 1,300 kips longitudinal, same as what Soldotna is designed for. And what I'm showing in this picture is it has nosing armor, so there's steel built into the concrete nose that's supposed to resist those local ice forces. And you can see this, the nose on Yukon River has not been successful in that regard. We've tried to fix it several times, but the ice force is just enormous and they just rip that steel out like nothing. So hopefully I made my 15 minutes. If I didn't, I apologize. If you have questions, certainly you can ask me if they're sort of bridge structural, but honestly, Mike Knapp, who is my colleague and we work together here in the same office, is probably going to be the person you want to talk about hydraulics or ice and design thicknesses and so forth. I go to him for those numbers. So any questions? Is anyone there?